All right, so that was our review problem. So let's go ahead and jump into 7.1, the definition of nth root and then simplifying nth roots and also Pythagorean theorem. Those are all things that we're looking at in this video. Okay, so first of all, in your notebook, you should have something where these symbols are basically kind of set up. So first of all, in this, we're trying to relate what is the nth root, and we also want to relate it to rational exponents because we're going to be talking about rational exponents in 7.3. So we're kind of relating this also to things that we're going to be looking at in 7.3. So roots and radicals. Okay, this symbol right here basically is what we call the radical symbol. Okay, and we know it as finding a root, okay? In rational exponent, the exponent is a fraction because rational numbers are a fraction, okay? So now let's get down to this part right here because we have this n right here. Okay, the first question in your notebook is actually saying, what is the nth root? Well, let's talk about that for a second. This n right here is what we call the index number. And that's what describing the root that we're looking for. So the nth root is finding the number, let's say the number raised to the nth power that equals the radicand. Okay, so now we just used a term here. I haven't even talked about what a radicand is, so let's talk about what the radicand is. The number inside of the radical is called the radicand. So down here, in this bottom example here, a to the m is equal to the radicand. Okay, now you guys, if we look over here on the rational exponents page, these two expressions are equal to each other. If I take the nth root of a, that is the same thing as a to the 1/nth power. A is still the radicand. And you can see that n is equal to the index number. So the big thing that we see here is that n, the index number, becomes the denominator of the rational exponent. Okay, so now down on this last one, we have that these two symbols are equal to each other. You can see that the only thing that happens here is now we have the radicand is raised to a power. So first things first on that, I want to show that this is one way of writing it, but we could also write this as the nth root of a raised to the m power. So those two things are equal to each other. And both of them are equal to this form right here of with the rational exponent. So you can see that n is the index number, and it's in the denominator, and then m is the exponent of the radicand. Okay, so now the next thing you have here is this whole select the correct answer if real or imaginary. So first things that we want to talk about is, I actually want you to go ahead and write this down to kind of make a connection. So you can write this off to the side because the real imaginary part isn't going to work as well. The real imaginary is actually going to go with what you have on page 55 of the original notebook. Those of you who've gotten the second edition, it should actually be nicer. But first edition notebook, this is what you're going to write on page 54. And then our next slide will cover page 55, which is combining the real and imaginary and some statements. Okay, so first of all, when you're simplifying an important root, remember we talked about the nth root is basically finding where the radicand, this right here, is equal to the answer raised to the nth power. So basically all nth root problems can be rewritten in this form right here, where a is equal to, or the radicand is equal to b to the n power. So like in the case of this problem, the 2 would represent the second root, which we also know this as the square root. And we don't usually write the 2 there, but for the sake of showing this connection, we want to have the index number. So this allows us to say that 16 is equal to 4 to the second power, which we know. Then in this case, we have an index number of 3. This is what we call a cube root. Any index number above 3 doesn't have a special name. It just ends up following that number. So 4th root, 5th root, whatever. But again, just like how with polynomials, we say linear, square root, or squared, cubic, and then we move on to 4th degree, 5th degree. It's just up to 3 that they get special names. So anyways, getting back to this, we can rewrite this as 125, the radicand, is equal to 5 to the third power, which is also true. So now what we want to be able to say here is, without calculators, we want to be able to figure out what the cube root of 216 is. So we would do 216 is equal to b to the third power, and we want to figure out what b to the third power is. Well, this is actually where using knowing like your numbers raised to powers, what those are equal to, is really useful. So 216 is equal to actually 6 to the third power. So that allows us to then take this number and say it's equal to 6. We know that 81 is equal to 3 to the 4th power. So again, we take this number and we can say that the 4th root of 81 is equal to 3. So on the I know I said we were going to get into the whole real imaginary thing, but you actually want to also be familiar with your squares, cubes, 4th powers, 5th powers to easily simplify things down. So you can see that 6 to the 3rd, 216. We have 3 to the 80, 3 to the 4th is equal to 81. These are numbers that where you're going to be able to simplify nth roots fairly easily. So you can try writing these down, or you can take a picture of it, or you can create your own table to be able to help you out. But these are things like kind of like your multiplication tables, where you want to have them memorized just to have a quick, easy reference for simplifying things. Okay, so now let's talk about the whole real imaginary. This is actually, we're going to go, for those of you who have the first edition of the book, you actually want to go ahead and move this to page 55. So this is where the real imaginary comes in. So if we think about this, we're talking about this symbol here, NA. Okay, so if n is an even number, so we're talking about, 2, 4, 6, 8, all of those, and a is greater than 0, we're talking about taking a square root of a positive number, a square root of, or the 4th root of a positive number, 6th root of a positive number. All of those make sense, because if we think about this, let's go ahead and call this b. Then we have a is equal to b to the n. Anytime that the exponent is even, regardless if b is negative or positive, anytime it is even, b is going to end up being positive. So, anytime n is even, whether b is positive or negative, that means a is going to be positive. So that means that our answer will be real, because we're always going to end up with a real number. If n is odd and a is greater than 0, this is also always going to be real. Okay, because we're really just talking about a is equal to b to the n, and n, which is odd, this one, which is even. Okay, you're either going to get, when you raise something to an odd power, you're either going to get a positive or a negative number. Both positive and negative numbers are going to be real numbers. So that also covers this thing of real. If n is odd and a is less than 0, that works because we know that a can be negative. So, and then in this case, a is positive or negative. And then finally, this last one right here, if n is even and a is less than 0, well, if we go back to this reference right here, where n is even, a is always supposed to be positive. So if we are setting up a problem like the fourth root of negative 16, we know that we can't have negative 16 is equal to b to the n power. So what happens here is we say that this falls into the category of imaginary. There's no real solution to this, so there's what we call an imaginary solution. And we'll get into more of imaginary numbers in 7.3. Okay, so now let's talk about the steps of simplifying the nth root. So, to simplify the, let's fill in these blanks here. So the first thing we want to do is simplify the radicand. So anything that is inside of the radical, we want to make sure that that's simplified as far as possible. And that includes actually writing numerical values in their factored form, because we actually want everything to have an exponent, and we want one variable, not multiple variables. So that's the first thing. The second thing, we want to pay attention to if the index number is even or odd, and if the numerical value is positive or negative, because this is going to tell us if the answer is real or imaginary. Okay, so now step 2 is divide every exponent by the index number. The quotient in terms, whoa, that's a really ugly cue. The quotient in terms of the whole number is the exponent outside of the radical, and the remainder is the exponent inside of the radical. And then you write your answer in the final, when it's final form, where it should basically be along the lines of, if we use a, b, and again, so a to the m, b to the n. Let's not use n there, sorry, because we're going to use that for our index number. B to the r, and then the nth root of b, a to the q, and b to the s, or something like that. Okay, that's what it basically should look like. All right. Now let's actually use real numbers here to be able to simplify this out. So we're going to start out first with numbers, and then we're going to get into variables. So first, again, remember it says we want to rewrite each each number in its factored form. So remember, this would be the square root of 216, which was 6 to the third power. And then this is just the square root of 6. And then in this case, anytime you have a fraction with the same radical in the numerator and the denominator, you can actually simplify this to 6 to the third over 6. And then remember, the next thing it said was to simplify it. So in this case, we can simplify this down to the square root of 6 squared. Now remember, this is a square root. Paying attention here, we're taking an even root of a positive number, so our answer is going to be real. So now what we want to do is 6, and then we're going to divide the exponent by the index number, and we get 6 to the first power, and there's no remainder, so there's no more of a radical. Okay, on this problem right here, we've got the cube root of 625 over 40. So 625 is equal to 25 squared, which is going to give us 5 to the fourth power. 40, if you look at that table again, actually isn't a number raised to a power. So what we're going to do here is we're going to break it down to numbers that we know it multiplies to. So 2 and 4, 2 and 2 here. Okay, this is what we call factoring a number down to its primes. And so what you can see here is what we have is 2 to the third times 5. So again, now we want to look at this. This is a positive number, and we're finding an odd root. So this will still be real. We want to simplify the radicand down. So we have 5 to the fourth over 5, which will give us 5 cubed, and then we have 2 cubed. And then we're going to do 5 to the 3 over 3 and 2 to the 3 over 3 because we're dividing those. And that is going to give us 5 to the 1 over 2 to the 1. And there's no remainder, so again, no more radical. All right, now on this problem, we have variables. Cool. So first thing we want to do is we're going to factor down 432. I honestly don't know everything that goes into 432, so because this is an even number, I'm going to just start with 2. And then this is 216, divide this by 2, and then we get 108. We can divide this by 2, and we get 54. Divide by, okay, we know 54 is 9 and 6. And now I'm running out of space, so then 9 becomes, let's see, 3 and 3. Then we have 3 and 2. Okay, so if we rewrite this out, we have the cube root, and we'll just do negative out here, and then we'll do 2 to the, we've got 1, 2, 3, 4, 5, so 2 to the fifth, and then we have 3 squared, and then we have x to the seventh, and we have y to the fifth. Okay. So this is an odd root of a negative, which means our answer is going to be negative. It's real, but it's negative. So this is the only time where we're taking a radical and we'll get a negative answer when we simplify it. So now what we have is negative out front, and we're going to have 2 to the 5 over 3, and then we have 3 to the 2 over 3, and then we have x to the 7 over 3, and then this gives us y. Finally, y is equal to 5 over 3. Okay, so in this case, you can see that 3 isn't going to go into any of these numbers evenly, so that means we're still going to have a cube root. Okay, so 5 divided by 3, our answer is negative here. 5 divided by 3 is equal to 1 2/3. This 2 is the remainder. This is going to be, this is what we're talking about, the whole number for the exponent outside. So this is 2 to the first, and then we have 2 squared with the remainder on the inside. 3 to the 2/3, there, it doesn't go in a whole number of times, so that means that we're just going to have 3 squared. So you can see that the basically the numerator of the mixed number is going to stay the exponent inside of the radical. X to the 7/3, we know that 7/3 simplifies to 2 1/3. Again, this is a remainder. So what we have is x squared, that is the 2 to the mixed number. And then we have x to the first power inside. And then we go with 5/3. So 5/3 simplifies to 1 2/3. So this gives us y to the 1 on the outside and y to the second on the inside. So then when we simplify this out, we get negative 2x squared y times the cube root of 4 times 9, which will give us 36 xy squared. All right, now this one, we have the fourth root of a positive number, so this is going to be real, and it's going to simplify out to a positive number. So we want to factor 1215. So I'm going to go ahead and just divide this by 5, and 1215 divided by 5 is equal to 243. And then, that's not a 3 there, sorry. And then this is divisible by 3. Actually, it's also divisible by 9. So let's go ahead and make these numbers smaller. So 243 divided by 9 is equal to 27. This is 3 times 3. This is 3 times 3 squared, 3 times 9. Okay, so this means we can rewrite this problem as the fourth root of 3 to the 1, 2, 3, 4, 5 power, so 3 to the 5th, times 5 times x to the 5th. Sorry, I'm at the bottom of the screen, so my handwriting is even worse. And I'm a little shaky today. And then y to the 8th. So this means that what we're going to have here is we got to divide these out. So 3 to the 5 divided by 4. We automatically know that this is 1, so 1 divided by 4, so it's still going to be the fourth root of 5. Then we have x to the 5 divided by 4 and y to the 8 divided by 4. Okay, so on these improper fractions here, 5/4 is equal to 1 1/4. So remember, this is the exponent outside, this is the exponent inside. 5 5/4 is equal to 1 1/4. So outside, inside, and this is equal to 2. There's no remainder, so there's not going to be anything on the inside there. So then this is going to simplify to 3 to the first power, and then fourth root of 3, and then we also have the 5 still. And then we have times x to the first power, and x to the first power on the inside, and then we have y squared and no y on the inside. So then when we simplify this all down, it should just look like 3xy squared fourth root of 15x. Alright, so here's some more example problems from this, where you can use these problems to basically write down your examples from the video under there. Whatever space you have on page 56 of the edition 1, or there should be a full page on edition 2. Okay, so remember, first thing we want to do is we want to break 32 down into its exponents. So 32 is equal to 4 times 8, which is equal to 2 squared and times 2 cubed. So 32 is equal to 2 to the 5th. Then we have x to the 16th and y to the 7th. Okay, so really what we can do here is, instead of writing it out as 2 to that fraction form, we can go ahead and think of it as, draw our fourth root here, and we can go ahead and do 5 divided by 4. 5 divided by 4 goes into one whole time with a remainder of 1. Then we can do 16 divided by 4. 16 divided by 4 is going to give us 4 with 0 remainder, so x isn't going to go inside of the radical. 7 divided by 4 is going to give us 1 with a remainder of 3. So then this is going to simplify to 2x to the 4th y times the 4th root of 2y cubed. Okay, again on this one, cube root of 27 is 3 to the 3rd power, x cubed, y cubed. Okay, so again, what we can think here is divide the exponent by 3. So 3 divided by 3 is going to give us 3 to the 1st power. Again, we have x, the exponent for x is 3, so 3 divided by 3 is going to give us x to the 1st power. The exponent for y is 3, so 3 divided by 3 is going to give us y to the 1st power. None of those have remainders, so this is blank. So then our final answer is 3xy. Okay, so what I'd like you to do is pause the video here and try to do these problems on your own and see how you do. And then you can start the video again and compare your answer to what I got. Okay, so you can see on these problems, 64 is equal to 4 to the 3rd power. Again, we're dividing these exponents by 3. So 3 divided by 3 gives us 1, 0 remainder, so there's not a 4 in there. 9 divided by 3 gives us 3, 0 remainder, so there's not an x inside of the radical. And then 5 divided by 3 is 1 with a remainder of 2, so we have y to the 2nd power inside of the radical. Then we simplify it down with getting rid of like the exponents of 1 to this expression right here. Now with 243, 243 is equal to 3 to the 5th power. 125 is equal to 5 to the 3rd power. And then you can see that we have a negative exponent here, so we actually want to simplify that down as well. So negative exponents move up to the top, and so it would actually be y to the 7th times y to the 5th, which gives us y to the 12th. So remember, you always want to simplify the radicand before you actually go and try to simplify the entire radical. So now in this case, we're dividing every exponent by 4. 5 divided by 4 is 1 with a remainder of 1, so that's why we have a 3 on the inside. 9 divided by 4 is equal to 2 with a remainder of 1, so that's why we have x to the 1st power on the inside, or as part of the radicand. Y squared, or sorry, y to the 12th divided by 4 is y cubed with 0 remainder. 3 divided by 4, it's not a whole number, so 3 is the remainder, so that's why that stays on the inside, and then we simplify it down to this. Okay, last thing, domain of radical functions. How do you determine the domain of a square root function? So we've gone over this a couple, well, it seems like multiple times in class, because remember we talked about that a square root, if it's going to stay real, has to be either positive or 0. That's actually true for any even root. So if we're doing the square root of, we'll just call this radicand because it can be any expression, then we have to do the radicand has to be greater than or equal to 0. So the domain of a radical function depends on the index number. Basically what it means is that if index number is even, then there's actually a limit to the domain. Then radicand has to be greater than or equal to 0. You have to do that, okay? So if the radicand ends up being a negative, then that means that your answer is imaginary. It's not on the real number line, okay? If the index number is odd, then radicand can be any number / expression. All right.